Okay. Okay, thank you very much for being here. Welcome to our lecture today, live from Chile, the greatest cosmic movie ever made, by Professor Keith Bechtol, who is an associate professor in the Department of Physics here at the University of Wisconsin-Madison. He is an observational cosmologist who uses the universe as a laboratory to study the fundamental nature of matter, energy, space, and time. His research includes discoveries of some of the most dark matter-dominated galaxies known and major contributions to the study of high-energy gamma ray and neutrino emissions. Professor Bechtol also plays a leading role in the commissioning of the Vera Rubin Observatory, which will soon revolutionize our understanding of the cosmos. He earned his PhD in physics from Stanford University, so welcome to the people here and those who are connected through Zoom. Thank you, Professor Bechtol, for being here.
Thank you, thank you. So I'm super excited to give this talk. I often talk to sort of astronomy and physics audiences, so I thought this is a really exciting opportunity to talk about what it's like to work on one of these big astronomy projects in Chile. So this is the Vera Rubin Observatory. It is just now finishing construction and is about to start its routine observations. So maybe the first question we want to ask is why build another telescope? Like why do we keep building bigger and larger telescopes? So how many people have seen this image before?
From Hubble, yeah.
Yeah, so this is one of the most iconic images, and I would say astronomy, but in science in general. So this is an image. It's a compilation of basically taking long, very deep exposures and multiple color filters with the Hubble Space Telescope. What they did is that they basically pointed at a blank patch of sky, right, just like a sort of semi-randomly picked spot, and they exposed the camera for 11 days. Right, just to see like what is out there, and it's this kind of incredible image of galaxies across billions of years of cosmic history, right? Because as we look far away, we're also looking back in time. Okay? And it turns out that this small patch of sky that was imaged by Hubble, if you compare it to the size of the moon, which is half a degree across, like you could cover it up with your thumb, if you hold out your thumb at full length, it's this size.
Oh.
Okay. It would take about 10 million photos like this to cover the full sky, and this took 11 days. So what's amazing here is that every smudge of light basically in this image is a galaxy, and if you count the galaxies and then extrapolate over the full sky, you'd infer that there's about 2 trillion galaxies that we could observe from the Earth. Okay, but it would take a really long time to do this with Hubble. Right. So you can think about Hubble as like a precision instrument for studying a particular astronomical object. But what we haven't been able to do until quite recently is the ability to take images like this, but do it over large portions of the sky, basically conducting a cosmic survey. And if you do this multiple times, if you can survey the sky fast enough, then that becomes a cosmic movie. Right. And that's what Rubin Observatory is trying to do. So it's located on a mountaintop in Chile, high up in the Atacama Desert, one of the driest deserts in the world. And it's going to revolutionize the way that we do astronomy, that we explore the cosmos. It will use the largest camera ever built that will repeatedly image the night sky every night for 10 years and create an ultra-wide, ultra-high definition time-lapse record of the universe. In that resulting movie, the idea is that this will bring the night sky to life in a way that we haven't been able to do. We will see not only these distant galaxies, but we will see asteroids and comets in our solar system. We will see pulsating stars and see the structure of our Milky Way galaxy. We will see supernova explosions where a star explodes at the end of its lifetime. And because we're seeing much more of the universe than we've ever been able to see before, it's possible that there will be surprises. And maybe that's actually the most exciting opportunity. So everything about Rubin Observatory is big. Okay, so this is one of my colleagues, Alana, who's been working on the project with me for several years. And this is the sort of the front end of the telescope, right? So the light would come in from this direction. This is the backside of the camera, it reflects off the mirrors, right? But you can tell this is a massive structure. right? Everything about this project is incredibly large and ambitious. And I'll give you a sense of what we mean here. So if you're trying to make this time-lapse movie of the universe, you need a really wide field of view. So this is the size of that Hubble Ultra Deep Field that you just saw relative to one of the sensors out of 189 on the full camera focal plane for Rubin Observatory, right? So we would be able to map, in a single image of the night sky, a region that is much, much larger, right, than that Hubble field. Because it has such a large mirror, it's 8 meters across, it can collect a lot of light, and that means you can see really faint objects in the distant universe. And so at the time that Rubin Observatory was being built, this is what what the wide field imaging surveys of the night sky were able to do. And this is representative of the data that Rubin is generating. Okay, so you just see much more of the universe when you have this deep exposure. And you can see the richness of the data. The other thing is that it's going to be very rapidly scanning the sky. So you can imagine this is like a map of the celestial sphere. And throughout every night, it'll take one of these giant images of the night sky, basically a digital photograph, about every 40 seconds. And it's going to be continuously scanning over the sky. So it would take about 3 nights to basically make one pass over the entire night sky visible from Chile. Okay. And if you do that every night for 10 years, you get 2.5 million such objects, or such images. Okay. It also means that each patch of the sky gets visited about 800 times. And that's why we call this a movie, right? It's not just a single still image. It's actually we come back and we visit it over and over again. So it's a huge amount of data. Because we had these repeat visits of the night sky, we will generate about 10 million notices of things that have changed in the night sky every single night. We'll generate 500 petabytes of image and catalog data. To give a sense of scale, like a high-end laptop is about a terabyte, right, of memory. This is 500 petabytes. That's comparable to everything that's been written by humans in all languages over all of human history. To give like a sense of the data volume. We are providing data access and analysis services to a global science community of 10,000 users, so international collaborators around the world. And because the data is so large, it sort of breaks the traditional model of astronomy, where like it used to be that an astronomer would write a proposal, they go to the telescope, they would observe their favorite target, they would take the data back and analyze it with their students. But what we're doing now is that we observe the whole sky visible from Chile every couple nights. And then we generate this enormous amount of science-ready data products. And then these users, in many cases, they will be logging on to compute clusters. They will be logging onto the cloud to access the data, because it's way too much data. You couldn't possibly store it on your laptop. Even a single night of images is 20 terabytes, which will fill up 20 laptops. And all of the science pipelines, basically the algorithms and the software that reduces the data, is all open source. And many of the packages have 50 or more contributors. So if you think about like in the culture of software development, this is a very collaborative model, right? Which I think really positive thing. So to start some of this up, the Rubin Observatory will catalog more stars, more galaxies, more supernova solar system objects in its first year than all previous astronomical telescopes combined, right? It's designed to be sort of this ultimate universe mapping machine. Okay, I mentioned this, it's just this enormous amount of data that's comparable to some of the largest data sets that we have. And the camera, it has so many pixels, it's like 3.2 billion pixels. It would take 400 high-definition TVs to show a single image at full resolution, and that's enough to cover a basketball court. So it's a huge amount of data, and we take an image like that every 40 seconds. Okay. So Rubin Observatory will catalog about 20 billion galaxies, right, which is more than the number of people on Earth. That's approximately 1% of all the galaxies in our region of the universe that we can observe. So it's like we're starting to, get to the level where we're mapping significant fractions of what is even possible for us to see. Most of those galaxies will be seen, like the light will have traveled more than 5 billion years to reach us, which means that we are seeing those galaxies before the formation of our solar system. Like that we're seeing those galaxies at a time that is even older than the formation of the Earth. In most of these galaxies that we see in the images will be about 1 billion times fainter than the limit of human vision. So even though we're looking at kind of a similar wavelength range is like our human eyes, we see further into the ultraviolet and further into the infrared, but it's about this, it's a similar range that overlaps, but the galaxies are about 1 billion times fainter. So the science is really broad, right? You can imagine that we are just creating this enormous data set, and then thousands of astronomers and also students, because there's an education public outreach component. Basically, they will have this enormous data. It's like turning the universe into a database, and then you download the particular segment of data that you're interested in. So there will be some people who are interested in, like great mysteries about the structure and evolution of the universe. There will be people who are interested in how our Milky Way galaxy formed. There will be people who are interested in, objects in our solar system, including objects that could potentially hit the Earth, right? It's basically designed so that we actually get a complete census of all of the potentially hazardous near-Earth objects in our solar system. And we can also see, potential surprises about how the universe changes over time, right? So people just download the subset of data that they're interested to analyze. Okay, so I'd like to talk a little bit about observing the night sky from Chile. It is strikingly beautiful. So Chile is now home to about 50% of all the astronomical infrastructure in the world.
Wow.
So it basically has perfect environmental conditions, and it also has had a sufficiently stable economy, political system. There has been years of technological and scientific infrastructure that has allowed this sort of ecosystem to develop. And so there's many observatories. This is just a subset of these. Rubin Observatory is this one. I'll show some maps that give a sense of where they are. And by 2030, it's expected that about 70% of all the global astronomical infrastructure will be in Chile, and specifically this sort of north region, a little bit north of Santiago in the Atacama Desert. And it's many different types of astronomical observatories. So for example, this is the largest telescope ever built. It has an over 30-meter diameter, the creatively named extremely large telescope. So whereas Rubin is designed to do a survey, this is designed to do study specific objects in detail from the ground. But there's also facilities that are using all different wavelengths of light. So for example, gamma ray astronomy, sub-millimeter astronomy with ALMA, studies of the cosmic microwave background with the Simons Observatory. You can see that these are like really different looking telescopes because they're all using different technology, right? And they're looking at the universe in different wavelengths of electromagnetic radiation, basically light. And they all have a different role in terms of helping us understand the universe. And Chile supports all of these different types of facilities. Okay. So why Chile, right? One is that if you're in the Chilean Andes, right, you're very high. You're above as much of the atmosphere as possible. And so this is basically looking down the ridge from Rubin Observatory. So from Rubin, you can see Gemini and SOAR, which is an 8-meter telescope, 4-meter telescope. So these are also massive facilities. But you're, in this case, you're actually like above the cloud layer. It is really amazing to be up there. It's really dry. This is a view. So when you take the transport from La Serena up to the ridge, this is that ridge line here. So SOAR, Gemini, Rubin Observatory. This is a lookout. But it looks like this as you're taking the transport up. It's very dry. It's one of the driest deserts of the world. And this is really important to be basically really high and dry. You want to be above as much of the atmosphere as possible, limit the amount of water vapor. Because if you look at the transmission of the atmosphere as a function of wavelength, this is the region of one of the highest transmissions, and this is the light that we see. So it's probably not coincidental that our eyes have evolved to see light of this wavelength, right? But if you go further into the ultraviolet, X-ray, and gamma ray, you basically need to do those studies from space because the Earth atmosphere is completely opaque. There's also a window that's open in the radio part of the spectrum, and so this is why we have radio telescopes on the Earth. But when you look, particularly in parts of the infrared, like this is all like water vapor absorption, right? A lot of these lines. And so we basically want to get above as much of the atmosphere as possible and have it as dry as possible so that we get the most light from the night sky. It's also really dark. This region of Chile has actually been designated as a dark sky sanctuary by the Chilean government to basically try to minimize light pollution to the extent possible. And so this is one of the signs that you see if you're driving on the road here. So the road to the stars. And it's actually named after the Chilean poet and Nobel laureate Gabriela Mistral, this dark sky sanctuary. So I put a bunch of text here, which we don't need to read all of it. But this dark sky sanctuary, it's the first international dark sky sanctuary in the world, and I mentioned it's named after Gabriela Mistral. It's 90,000 acres of this mountainous terrain that's been protected, and there's 4 major astronomical facilities that are located here, including Rubin Observatory. Okay. And so what basically, like the way that something like this happens is that this land was basically set aside by the Chilean government to allow ARA, which is the organization that was doing a lot of this astronomical research and basically building up a lot of this infrastructure to basically work in this region of Chile. And there's been partnership over many years to basically ensure that this remains a world-class site for astronomy, and that includes basically this dark sky sanctuary status and parts of the Chilean government, basically departments that are dedicated to maintaining this. So if you look at the history of professional astronomy in Chile, so it's worth mentioning that there have been people in Chile looking up at the night sky in wonder for time immemorial. But in terms of professional astronomical research in Chile, there's sort of a couple key areas that people point to if you look at the histories of this. So one area is around the mid-1800s, and that was when there started being science expeditions to the Chile. They were initially looking at specific astronomical events, like the transit of Venus across the sun, which allows you to measure the size of the solar system more precisely. So there's like some specific expeditions that were being done, but also they started systematically exploring the mountains and identifying some of the best sites to build observatories. And then the National Astronomical Observatory of Chile basically bought some of that equipment and founded a first observatory in the 1850s, which was one of the first in South America. And then, so there was a next phase that began around the 1960s. So what happened is that the director of the Chilean National Observatory visited the United States and began talking about the opportunities for partnership. And then what you saw is that throughout the 1960s, you saw ARA, which is the Association of Universities of Research and Astronomy, basically designated a site, Cerro Tololo Inter-American Observatory, which is basically on the mountain over from Rubin Observatory. Designated that site. The European consortium of countries designated LACIS, and then private institutions also got involved. For example, the Carnegie Institute for Science established Las Campanas Observatory in 1969. And then what happened is that then, by around the year 2000, you started seeing larger investments, basically like billion-dollar scale projects that were starting to be built in Chile. And recognition of additional sites that were even better. So, like for example, Paranal Observatory, Gemini at Cerro Pachón, which is the ridge where Rubin is located, and then Alma Observatory is a billion-dollar class facility. And this was again just a major investment and started getting radio astronomy involved as well. This is the first stone ceremony for Rubin Observatory in 2015. This is the president of Chile who's there. So there's been this history of partnership. This is the NSF director, France Cordova, who's there. So this is the geographic lay of the land. So if you're going to Rubin Observatory, you fly into Santiago, and then you take another hour flight north to La Serena, which is near Coquimbo. So Coquimbo is a more sort of industrial port town. La Serena is more like a beach resort kind of place. It's a place where many Chileans and Argentinians like to go to vacation. It hosts the base facility. So there's a massive compute cluster here and a bunch of offices where people work. And then there's basically there's housing. I'll show a map in just a moment. So like many of the professional astronomers who work for Rubin Observatory basically work and live at this base facility in La Serena. And then there's the summit facility, Cerro Patron, right, which is where the observatory itself is located. And that's about a 2-hour drive inland. This is a map of that base facility. So all of these are houses. So I'd say within Rubin, it's like roughly half and half of people who have chosen to live like on the Recinto, and people who have chosen to live just in La Serena. Many people have taken it as an opportunity to learn the language, get more involved with the community rather than staying on the compound. This blue is the office buildings. And there's a grocery store here, which is where I go. And then this is at the summit. So this is Rubin Observatory, and then the casino is here. So this is where we get food. So there's basically chefs that work at the summit and provide food. On any given day, there's about 80 people who are working at the summit during the daytime, and about 20 who are working, who are staying overnight. So there's the Hotel Patron here. So it's about 3 kilometers to drive from Hotel Patron to the summit. And so basically we sleep overnight, we work all night, we sleep during the day. We have blackout blinds so that we can sleep. And then further down the ridge is Gemini and SOAR, right? So there's basically, this is something that was built up over several decades of infrastructure to kind of have this facility. And then that data, it's so much data that they had to build like dedicated data transmission lines from the summit to connect to the global internet backbone. But there's basically like cables that go underneath the ocean, right? And they take the data from Chile up to like there's a data facility at one of the US national laboratories based in California, SLAC. And then it's so much data that we've also partnered with data facilities in France and the United Kingdom to process all of that. Right? It's a huge amount of data. And the whole ecosystem is very involved, right? So there's the Rubin Observatory construction project. It's a $1 billion scale kind of investment. The bulk of the money comes from this has a better, larger font, comes from the US National Science Foundation and from the US Department of Energy Office of Science. So there's a construction project which is responsible for designing, building, commissioning the observatory, and then actually running all the observations for the 10-year survey. And then there's the science community, basically the science community. So all of the data gets collected, processed, that becomes available to a global science community. The science community is many thousands of astronomers and physicists around the world. And so they have organized into different science collaborations to basically focus on different scientific questions within the data set. But then there's also been like organizations that were needed to basically get the project off the ground. Like it actually took like an investment of about $30 million to start fabricating the mirror, because the mirror took 7 years to build. And so there was a donation from private donors that allowed that initial construction to get started. These are the non-federal funding. And then there's various like oversight committees. So it's like quite a complex ecosystem. For me personally, I both work for the construction project, and I'm also, I just started a term as the deputy spokesperson for the largest of the science collaborations. We have partners around the world, right? So the United States is the bulk of the funding, and then Chile is the host, right? Which has all the base and the summit facilities. But then there's about 30 countries around the world that are contributing, various expertise, access to other facilities, data processing, and the actual the components of Rubin Observatory have been constructed by, contributed by different vendors from around the world, right? So we have contractors, like the dome was made in Italy, all the infrastructure for the telescope itself, like the actual metal of the telescope, is from Spain. So we have partners around the world that have contributed. There are still challenges, when we think about, are we really being as inclusive as we could be in sort of all aspects of the project? So for example, Chile has very high representation in terms of a lot of the engineering and the construction staff that work for the project. But one of the places where we're still working on is that if you look at the composition of, this is the largest of the science collaborations, Chilean scientists are only 2%.
Yeah.
Right, which is unfortunate because the facility is located in Chile and there's all this expertise. The Chilean astronomical community has been historically more engaged in other aspects of the science, but this is one of the science areas that's the most funded and the most sort of supported, and is sort of most likely to yield sort of like Nobel Prize scale discoveries, if you can imagine that. It's sort of most prominent or most visible in that respect. And so this is an area where we would like to kind of continue to grow that partnership. Yeah, this is a picture I took at the summit. You can see this is the road that you take to get up. This is taken near the Hotel Pachon. And so there are ranchers who have lived on this land, and the agreement was that when this became a dark sky sanctuary and became, sort of the host for these astronomical facilities, that the ranchers would be allowed to stay. And so sometimes we see the horses. We also see incredible diversity of wildlife. So condors, hummingbirds. This is our all sky camera. But this time a bird perched right on our all sky camera. This is what we use to, just to get a quick check of the weather. Biscachas. This is a picture I took of a tarantula. I walked, so you work all night, and so I went out at night. Was walking to the truck to drive down to Hotel Pachon. There's this is like hand size. Tarantula. You also experience all weather conditions. So, for over 300 nights a year, it's, clear skies, basically, fantastic conditions for observing, but it does snow in the wintertime. This is all ice, right? That's collected on our weather tower. And this is when we have a snowstorm, right? We don't want any of the precipitation, any of the water to fall down on all the delicate equipment inside the dome. So how would you like to have this job, right? These are some of our engineers who are inspecting the dome to make sure that all of the ice has melted and there's no residual moisture, right? And so this is looking over this guy's shoulder, and you can see the trucks down in scale. So I mean, these guys are well over 100 feet in the air, working on top of the dome. So I mentioned that on any given day, there's about 80 people who are working at the summit. And there's not enough room for everyone to stay at the hotel at the summit. So what we do is that we have basically these tour buses, and we have transports that are going up and down. So a lot of the people who work for Rubin Observatory, they will go up at 6 a.m., right? Because it takes 2 hours to get there. And then they will leave at the end of the day, at 5 p.m. And so it's hard work. It's hard work, right? And so we have just an incredibly dedicated staff that has made a lot of this work possible. It is not easy working in this really beautiful but remote environment. This was a picture taken a couple weeks ago for the 18, which is the big national holiday in Chile. So there were staff that continued to work at the observatory so that we were able to keep observing. This was like right at the end of our on-sky commissioning campaign, when we were trying to collect, final data sets. But in general, we operate 365 days a year. Like the cost every night of observing is about $100,000, right? Just to give like a sense of scale for the amount of investment. And so we work every single night. And so you can see here kind of a mix of professional astronomers, managers, observing specialists, people who are working, working the kitchen and the infrastructure at the facility, engineers, right? They had nice food, including Chilean empanadas. I love the food there. It's so good. It's fantastic. And then there's even time to learn traditional dance. So, you have our stylish safety vest. So the four women in this movie, all different nationalities. So building Rubin Observatory, how do we actually build something like this? Okay. So in terms of a brief history, so the idea for this is over 20 years old. Like if you go back and look at the very first proposals, they go back to around 1998. And then by 2010, basically every 10 years, the national astronomical community gets together and decides what are the top priorities, right? If we have to pick, just a handful of projects that we're able to support, which are we going to do? And in 2010, they selected Rubin Observatory as the highest priority. And then the formal construction started in 2014, but there had already been well over a decade of advanced design and development work for that. This is a more detailed timeline in case people have questions, but basically, years and years of work. The site selection started in 2003 and was formalized in 2006. And so this is when Chile became the site of Cerro Patron was officially selected. I started the project in 2016, so I've been working on it for almost a decade. So what makes Rubin possible is basically this confluence of enabling technologies. Basically, you need the ability to build 8-meter mirrors that you can control the surface at nanometer scale precision. Right? Not easy to do. You need this mosaic of high quantum efficiency CCDs. Those are the actual sensors that record the light. So without that technology of basically that imaging digital technology, you can't build this, and it needs to have really broad wavelength sensitivity. You need to have an enormous amount of computational power. So if you think about this, this was being proposed in 1998, right? And the computing technology to manage this data did not exist, right? So basically, the visionaries for this project had to envision what technology would look like 2 or 3 decades later, and basically build the thing that would be able to utilize those technologies. This is what it would look like on a typical day during construction. So this is inside the summit facility. So we basically had a staging area, and all of the individual components were being tested before they would go up inside the dome and installed, right? And so what we would do is that we would take all of our different partners from around the world, be sending the components to Chile. We'd bring them, we test them, and then we'd install them, commission, make everything work. So basically, my role in the project has been sort of overall scientific oversight and coordination of the commissioning process. So this is the mirror, for on the scale. So it's 8 meters across, right? Made of glass. It's this size because it's the largest monolithic piece of glass that you can fit through the tunnel that goes up. You have to pass through this tunnel. So it's like ship in the bottle. Right, you got it. This is basically the largest structure. You basically have like a few centimeters of clearance. So this is it going up to the ridge, going around the final bend. I love this picture. And then this is coating the mirror. So it goes in. I show these pictures in part because I think it's really helpful to see like what all the people are doing. Like it's really helpful to get like a sense of scale for the people. This coating plant was made in Germany, and we have the coating in the base facility because we actually need to recoat the beer periodically over the 10 years of the survey. All right, so here's the part that's going to be really cool. That's the full reflective mirror. All right, and then once you've got the coated mirror, this was October last year, right? You get a sense for the number of construction workers and engineers that are required, right? So now it's been coated and it's going up on a lift. It's not an elevator because it's not for people, it's a lift. This lift was made by a contractor in Wisconsin, just outside of Milwaukee, right? So there's a little piece of data room observatory. So it goes up on the lift. And look at this, you see like we actually have to lift this up so there's space to get it, get it inside the dome. And it rolls in, it's like rails, like on a train yard. Right. All this is very sped up, right? Like this procedure took many hours. Moving very carefully. Right. Submission. This was good. Take a group photo. Right, and this is what it looks like. So if you're standing next to an observatory, this is what you would see. And it had it's almost like mind bending what's going on here because there's actually 3 different mirrors. And so the light bounces off the primary mirror, hits a secondary mirror, and then hits a tertiary mirror, and then finally goes into the camera. And that's an optical design to get this really large field of view. This whole thing needs to move really fast, right? So it's like a point and shoot camera, right? Except for you've got to move this 3,000 kilograms of steel, right? And it's got to move really fast to basically observe the night sky efficiently. And so we did a lot of testing. This is like engineering tests, like during the daytime, right? We spent about a year doing this, of just driving the telescope all day, making sure we understand how it would move, making sure we would understand all of the inertial forces and all of the components. Because all these individual pieces are really heavy. So to give a sense, like the whole telescope is about 350,000 kilograms, but the mass of the mirror is 16,000 kilograms, right? So when you move it around that fast, it generates a lot of inertial forces, right? And you've got to be able to control the surface figure. So what we're doing is that we're basically like the silver on the mirror is about 60 grams of silver, and we're trying to keep that like in optical alignment at about tens of nanometer precision. Okay. Throughout the night, as temperatures are changing, as the orientation of the telescope is changing, right? We've got all kinds of dynamic systems. So like, I guess what I say is like, the telescope is not something that like you build once and then it's just like done, right? It's actually like a living, breathing object in some sense, right? Like it changes every night. And so it has like so many different subsystems that all need to work together. This is the largest convex mirror ever made, right? This is the secondary mirror. Let's get this just in the interest of time. This is the camera, right? So it's about the size of like a manhole cover, right? This is being installed, one of the individual rafts, because it's 189 individual sensors. This is the full focal plane. Again, it's 3.2 gigapixels, right? Like your phone's like megapixels. This is the largest lens ever made for astronomy. This is on the front of the camera. This is what it looks like. This is the engineering team at SLAC that helped put it together. It was transported by airplane and then went up to the summit very carefully by truck. And then had to be installed. So basically there was a moment where we had to bring like the telescope component and the camera components together. And then at that point, we're ready to install it. And so this is like what one of these lift procedures looks like. Again, this is like sped up. This would take like a whole day, like 8 hours. but you basically have to like move in these components with, millimeter scale precision, so that you don't have any collisions. These are, massive objects that weigh thousands of kilograms. And so we have dedicated cranes inside the dome to help do all that movement. I'd like to show a video at this point, just to give a sense of like what it's actually like to work on a project like this. This is on the night, this is the 24 hours when we were going to take the first night sky images.
Hola, buenos días.
Buenos días, Oscar.
Bien, vamos a comenzar a revisar la actividad que tenemos para el día de hoy.
Viendo.
Ya partamos inmediatamente entonces con Freddy. Freddy, buenos días.
Buenos días. Estamos en posición de comenzar ahora inmediato el cambio de filtros. Y la tarea es larga, por eso me importa dejarla corriendo ahora para salir antes del almuerzo y poder inicializar el aceite al mediodía. Para esto tenemos 4 personas: Mario, Claudio Araya y Rodrigo Rojas en la grúa. También voy a dejar yo y Gladys. Por eso me importa dejarla corriendo ahora para iniciar un propio de prueba para almuerzo. Yeah. Okay, we are switching this because of Gemini or the moon. I just want to understand the science behind.
Well, we need to filter in the first look campaign.
Okay.
Alex, tu m'entends? What the life?
It's like a better view, like I'm down there, I can actually see what's going on.
Great, thank you very much.
Parker,
Buen día.
hola, buenos días.
Hoy necesito instalar cable de power a la proyecta.
Ah, ya, ok.
Está desordenado arriba. ¿Ahí? El cable da lo mismo por fuera. ¿Está bien? Después tenemos los minutos. Los últimos. Dos para.
I told the management that calibration will be ready for
Can you hear
the
it okay?
first photon. And they didn't believe me, but if we can turn it on today, then I'm correct. Yeah.
La tarea principal para el día de hoy es con Anwar Zamora y con Doug Neal. Vamos a subir e inspeccionar todo lo que es el sistema de lubricación de motores, piñones, cremalleras y rodamiento.
Estamos verificando la posibilidad de instalar, reinstalar los fusibles una vez que Marco de Face y Lorenzo puedan determinar qué pasó con la fuente. Así que vamos a reinstalar los fusibles y hacer posteriormente una prueba.
What you might have noticed is a tremendous frenzy of activity.
Entonces necesitamos dejar el
It's our
dispositivo
project
dentro,
manager.
cerrar para poder desde afuera, sin abrir el gabinete, censar la corriente.
So, I mean, Freddie's been balancing the telescope. It faulted, so now he has to recover it. Acá venimos para el Hanover para poder usar el sala de control. En este momento está bloqueado por otro sistema.
Ya.
Voy. Vale, va. ¿Estamos listos para izar para arriba o no? Yo voy para arriba.
It's like this every day.
No. Viendo 700. Y ya le había dado a mover el segundo a 700, van a quedar los 290 a 700.
is down in La Serena. Base facility. This is the bus. People are gathering to do it, to go to the watch party.
We're really happy that all of you made it to come here and that we can have this great moment together. Ellos nos van a avisar cuando está el momento de prender fotos. Gracias.
It's only two volts left.
Es emocionante que después de tantos años, 10 años, por fin vamos a ver la luz.
We're taking an image, we are ignoring the goal. Now you go, 30
seconds.
Don't touch, don't touch.
Okay. All right.
Don't touch.
El cliente llegó. Sí. Dale.
And 10 years of construction, this is 20 years of an idea. This is a first of its kind in so many ways. I think there's probably about 400 people on our builders list, and there's probably an equally amount that have participated in some way building this phenomenal observatory.
Yeah, thank you.
Hundreds of scientists and engineers, managers, wives, families, they all sacrificed to get here. It's really great to see.
How many channels can you work?
Get kind of emotional watching it.
Yeah.
Yeah, so it's like that every day.
No.
Okay, it's been like that for 10 years, try to get the thing working. This was the moment, so I was in the control room when we did the first images. I was actually like choosing like which target we would observe. And so this was this is Carla and Gonzalo, right, who you saw in the movie. Marina is here, right? So these are all the people who are getting things working during the day, right? But this is the moment where I'm like, oh my gosh, like now I have to make this thing work on sky, right? But we were able, like within a few minutes, we were able to get the telescope in focus, and then everyone is really happy, right? So there's still like months, many months of work to do, but at this point, like we knew that the telescope had been assembled close enough that we were going to be able, like it was going to be able to work. It was a matter of fine tuning. So I've spent like a lot of the past year in Chile and like working many like night shifts. I basically was in nocturnal mode, writing a lot of the software to drive the telescope and trying to coordinate a lot of the activities. This is like we took a lot of like group photos. I think it was just like this really powerful experience for a lot of people who are working on the project. So this is the night that we finally took over 500 individual exposures of the night sky on the same night. So we were basically like running as an astronomical observatory. And we took the data that's going to show up in some of the images here. So I want to show you what some of those images looked like. So this is one of the images that we took of a region on the galactic plane of our Milky Way. So I designed all of these observations. Like I wrote the software to basically pick the targets and kind of the composition. But basically, we're seeing a region that these are like some of the brightest nebulae regions, and there's just a huge number of stars in the background. You see dust lanes. This is like the dust that will later like condense and form planets, right? Where you see these glowing nebula is where you have the radiation from hot young stars that's illuminating the surrounding gas. Just in the interest of time, let me show. Actually, well, this is a good one. This is another region that we observed. This is a region near one of the largest clusters of galaxies. So what I like about this video is that it basically kind of gives like a sense of the scale of the images, right? You just like keep on zooming in, you just go further and further. You see major galaxies. So this is basically this is taking data from about 1,000 individual images that we took. Size of the focal plane, so basically a single image. Right, this is zoom ins just to give a sense of what it looks like and the richness of the data. Right, so there's an enormous amount to explore here. You can just see there's a tremendous amount of detail. And now our job is to like use all this data to find out all the patterns.
What does it mean?
Right, it's just like this incredible wealth of data. So again, most of the galaxies that we're seeing are, we're seeing them billions of years in the past. We're seeing objects that are a billion times faint to the limit of human vision. And one of the things you can do, I talked about how this was like a cosmic movie. And so we cleaned up the images a little bit. And if you actually were to go back in something closer to the raw images, if I blink back and forth, you see these little streaks appear. So what's going on here is that we take successive images of the night sky about 40 seconds apart. In each one of these strings here is like basically a set of dots. And these are actually asteroids in our solar system.
Oh,
right. And so because we take images with different color filters, you can see that basically like it's like a black and white photograph in each of the different color filters, which is sensitive to a particular wavelength of light. And then to make a color composite image, we color those different filters like red and green and blue. And so what's happening here is that we would take basically sequences of exposures in the different color filters, and then they look like these streaks. So basically, like one of my roles was to like just design the observations so that we could do that. And this is what we mean by like a cosmic movie, right? Is that you can basically watch all these asteroids moving. And there's lots of them. Every one of these dots is one of a new asteroid that we discovered. So we took this data over a period of about a week. And then this is what it would look like in terms of where they're located in the solar system. Yeah, so that's it. We're about to start the cosmic movie. Hopefully later this calendar year, we'll just get into steady state observing, and then we'll do that for the next 10 years.
Thank you. We have like 4 minutes. So any questions?
Yeah, sorry. I feel like
No.
I hadn't given this talk. So, yeah.
I have so many questions. It's just amazing presentation. I'm wondering what given that the electromagnetic spectrum is only part of it is visual, and it's only in that visual corridor that Chile has any comparative advantage, correct?
Oh,
So I'm just wondering how, I mean, it's really interesting. I'm from Chile, and I know that the Lolo has always been this, amazingly important.
Yeah.
The whole thing is very important to Chile, but I just sort of wonder why beyond the visual spectrum it matters that it be Chile.
Yeah, so part of the, so for studies of the cosmic microwave background, which is the oldest light in the universe, we're talking like 400,000 years after the Big Bang, right? That's kind of in this like gigahertz frequencies, like centimeter type wavelengths. And this is extremely sensitive to water vapor in the atmosphere, right? Basically, like the only places that you can do cosmic microwave background astronomy from the Earth are basically places like Atacama Desert or like Antarctica, right? Because you need extremely stable atmospheric conditions. It needs to be extremely dry. And so basically these facilities like Simon's Observatory, CMB, ALMA's also sub-millimeter, you need it to be extremely dry. So you can see that the environment here, even compared to Cerro Pachon, there's no vegetation here. Like in Pachon, there's still like plants and animals. Here, it's like, it's just totally dry.
And just to follow up.
Yeah.
I guess this should be more for this one than Bechtol, but does the lithium industry, the increasing activity around lithium mining in the north of Chile affect these projects at all?
I haven't heard specifically that's been an issue, but most of these facilities are in extremely remote locations, sort of by design, because it has to be so dark. I haven't heard that there's been a specific conflict with any of the mining. Yeah, it's a good question. Yeah.
I have a quick question.
Yeah.
So the 70% of
Yeah.
these observatories in Chile like really struck me, and it made me think. Does that then mean that the north hemisphere sky is not observed in this? I mean, maybe I'm
Yeah.
asking a really
No,
uninformed.
it's a great question, great, because you can't see the entire, if you're a ground-based observatory, you can't see the whole celestial sphere from
Right.
any one latitude.
Correct, yeah.
Basically. So that's correct. And so Rubin Observatory, like we will try to map it like as much of the sky as we can from minus 30 degrees latitude. Right, but there are parts like we can't see, like the Big Dipper, for example,
Yeah.
right? So there are like regions of the sky that we can't observe. I think part of the concentration of observatories in the southern hemisphere has actually been intentional in the sense like we want different facilities using different wavelengths of light to be able to see the same region, right? And for example, like the extremely large telescope is going to be extremely powerful, but you have to know where to look, right? It's not a survey facility. So by having both the ELT and Rubin in Chile, Rubin can act as like the finder, but basically say like, hey, we found this like extremely rare, exciting object. Can you take a closer look at it? Right. So like what's going to happen is that a lot of these observatories are going to be doing surveys, but many of them actually will be specifically responding to notices. And it may be that in the future, a lot of this actually ends up being like robotic in the sense that there will be like, digital processing, send signals to other observatories, they begin observing a new target. So it's all like a lot of that infrastructure is now all being coordinated with like a lot of cooperation between the observatories. Yeah.
Thank you very much for your time. I really appreciate like how clear it was a presentation to us, because presenting this topic for an audience who doesn't like know the topics of physics. So it was very interesting to see not only like the place of Chile in Latin America with this industry of astronomy, which is also very international. Like, thank you very much. And those images, yeah.
Well,
We'll take them.
yeah, thanks.
Thank you.
Yeah.